Okay, so we're going to talk about divergence and curl, and we're going to start by looking at just two functions in two dimensions, okay? And of course, we do these things in three dimensions, ultimately. Matter of fact, the curl needs a third dimension. So when we do the curl, we're actually going to have to consider rotation, and from physics you know that rotation is represented by a vector in the third dimension, right? So that's a connection that you can make. Now, people that haven't had physics and haven't done rotation and right-hand rule and all that stuff, angular velocity, angular momentum, etc., torque won't necessarily relate to that, but you can. Okay, and that'll be useful too. Okay, well, anyhow, this field now is always in the direction away from the origin, right? Well, you can verify that yourself, but it's like this. Okay? And if you go further out, it gets bigger in proportion to how far you are from the origin. So in any circle, this field has constant magnitude, and the magnitude is always the distance of the circle from the center. So on this circle, these points all have the same distance from the center. The vector always has the same magnitude. And on this circle, we're roughly twice as far from the center, so the vectors, if I drew them proportionally, would have twice the magnitude. Okay, maybe I exaggerated a little bit, but you get the idea. Okay? So somehow this field is emanating out from the origin. Okay? So it diverges from the origin. Okay? Starts here and diverges out. And it's much like a gravitational field. Gravitational field, of course, would be inward, and it would get smaller as you go out, but it would still be radial. And it has a negative divergence from the origin.
So it would converge towards the origin?
Yeah, but you don't talk about conversion.
Okay.
You just talk about divergence, and it's positive or negative.
Okay.
Okay? Because it's not divergence in the sense of a divergent integral or a divergent sequence. So you don't want to really go with divergence and convergence. It gets you too much into, it triggers that context in your brain, and it's not. Okay? Has nothing to do with that. This is nothing directly. Okay? So anyhow, this field, on the other hand, also has the same magnitude at every distance from the origin, right? So I could draw a circle around the origin, but, okay, out here, x is 1, y is 0, right? Or x is, if this is a unit circle, x is 1, y is 0. And we're not putting a scale on it. But it's like this. Up here, x is 0, y is 1, or whatever. But you got a negative y, so you got this, right? Now you need to sit down and work this out yourself. But at every point, this field is perpendicular to this one, right?
Should be.
Huh?
Should be.
Well, what's the dot product?
0.
Yeah, negative xy plus xy, right? So it is perpendicular. Okay, and this one is tangential. Okay? And of course it gets bigger in this case as you go out from the origin. And getting bigger as you go away from the kind of source point or central point or whatever is not typical. Typically things in physics get weaker as you move away from the source, right? Okay? But now we can draw a similar picture. And of course, if you want the thing to get weaker, you can just divide by x squared plus y squared, right? That wouldn't be a reciprocal square because, of course, the magnitude of this is the square root of x squared plus y squared. If you divide by the cube root, or the 3/2 power of x squared plus y squared, you get an inverse square. And then this would mimic a gravitational field, except you'd want to make it negative so it goes inward. It would also mimic an electric field. From a positive charge, the electric field is away from the charge. Okay? For negative charge, the electric field is toward the charge. It's because positives repel positives and negatives attract positives. Okay? And we haven't talked about that, but you should know that from general science. Okay. Anyhow, then you will know it from physics. You'll know it way better than you really want to. No, you really want to. What kind of engineering you want to go into?
Probably mechanical.
Yeah, well, yeah, you're gonna need some classical mechanics. Maybe not, but you're gonna need this stuff. You'll see it. But you'll especially see all the stuff we're doing in physics with rotations and right-hand rule and right-hand rule and torques and all that stuff. Okay, so anyhow, there are two examples, right? Now what would you say about this field? This one diverges from the origin. What's this do relative to the origin?
Sort of diverges.
It what?
It sort of diverges.
It doesn't go away from the origin. It's always perpendicular to the radial line.
But it gets larger as you go away from the origin.
Well, it does, but that's not what it, with respect to the origin, what's happening? This is diverging from the origin. It doesn't have to get bigger or smaller. It's diverging from the origin, right? What's this sucker doing?
It's not. Well, it's staying perpendicular to the origin.
What's perpendicular to the origin?
The vectors.
You can't be perpendicular to a point. Perpendicular to a radial line, maybe. What's this kind of look like from physics? Anything in that picture remind you what you're seeing here?
Yeah. Okay. So the velocities get...
Those would actually be velocity vectors for points on this wheel, wouldn't they?
Yeah.
You go twice as far out, it goes twice as fast. And, so we could be talking about this bolt here and this bolt here, the path and velocities of this bolt, right? Okay? So what we have is rotation about the origin, okay? This field is rotational with respect to the origin. Make sense?
Mm-hmm.
Okay. Another way of visualizing this, now this wouldn't be a good field for the model, but if you have a little paddle going around circulating at the origin in water, it causes the water to rotate about this point. You got like a vortex around this point, right? Now the field would get smaller as you go out, okay? And the extent to which it gets smaller depends a lot on the viscosity of the liquid and other characteristics, depth. And of course, since we're in a plane here, but you could think of a rotational field, a uniform rotational field in a cylinder, right? You model that in just a plane, as long as you don't have anything going in the z direction. Okay? So, two different kinds of fields, a divergent field and a rotational field, right? Okay? So, you know, I start with this example because, you know, when I was taking multivariable calculus, even some physics course, I forget where it was, but it wasn't in multivariable calculus because I think a graduate student tried to answer the question, what does a curl mean? And he gave some sort of abstract definition that I knew related to circulating fluids or something, but it wasn't simple enough for my feeble brain to comprehend in the context in which we were working, which was in electromagnetism. Okay? Now, a couple of simple examples in electromagnetism that we'll see before we dive into electromagnetism will tell you exactly what that means. Got a current in a wire, the magnetic field circulates around the wire. Okay? So, you know, there are simple examples that he could have pulled out, but a graduate student, you know.
Straighten your hair? No.
A graduate student's case were extremely good, but he didn't give a good explanation of what curl meant. So anyhow, I've always tried to give a really concrete explanation of circulation and divergence. Okay.